We will now discuss directional derivatives. So first, let's recall the first order partial derivatives of the function z equals f of xy. They are defined to be f sub x, the partial derivative with respect to x, which is the limit as h goes to 0 of f of x plus h with y minus f of xy divided by h. And then the partial derivative of f with respect to y, or f sub y, could be the limit as k goes to 0 of f of x, y plus k, minus f of xy divided by k. So with the partial f sub x, we added a little bit h in the x direction and looked at that difference quotient. And with f sub y, the partial derivative with respect to y, we added a little bit k in the y direction and again looked at that difference quotient. But in reality, the x direction and the y direction are arbitrary. We should be able to define a derivative in any direction, and so that will be called the directional derivative. The directional derivative of the function f at a point r, so r in this case we're going to think about as being the vector xy, in the direction of a unit vector, say u, is going to be d sub u, which is saying we're going to take the derivative of f in the u direction, and that's going to be the limit as h goes to 0, f of r plus h times u minus f of r divided by h. And so here we have another difference quotient, but instead of adding a little bit in the x direction or adding a little bit in the y direction, we're going to add a little bit in the u direction where u is a unit vector. And so that allows us to look at the derivative in some arbitrary direction. Now, this directional derivative exists provided that the limit exists, just like the x and y partial derivatives. There's actually another way that we can rewrite this definition. We can look at it as the derivative with respect to t of f of r plus tu evaluated at t equals 0. So in this case, what we're doing is we're parameterizing a line that starts at the point r and then goes in the u direction. And then we're saying we're going to take the derivative of that single variable function and look at it when t equals 0. So I want you to note here that the partial derivatives fx and fy are actually directional derivatives. They're directional derivatives in the directions 1, 0 and 0, 1. So if you look at the definition of the directional derivative and you let u be the vector 1, 0, in fact, what we have is the definition of the partial derivative with respect to x. Or if you look at the direction 0, 1, then the directional derivative is actually the partial derivative with respect to y. Now this gives us a definition for the directional derivative, but it doesn't really give us a way to calculate the directional derivative. So let's look at a theorem. And that theorem says if the real valued function f is differentiable at r and u is a unit vector, then the directional derivative d sub u f of r exists and is given by the gradient of f at r dotted with u. So this says that the way to calculate the directional derivative is to first find the gradient and then dot it with the u direction. Okay, so we can prove this using the definition of this directional derivative where we thought about it as being on a parameterized line. Okay, so we can say, what is the derivative of f of r plus tu and we can take that derivative using the chain rule. So here that's going to give us the gradient of f of r plus tu dotted with the derivative of r plus tu. So dotted with the derivative of r plus tu. Well, in fact, that derivative of r plus tu, okay, is just the derivative with respect to t, so that's going to actually give me the u vector. Okay, so now if we want to take this derivative of f along that line, r plus tu, okay, and we're going to evaluate that at t equals 0, because that's the definition of the directional derivative. That's going to be the gradient of f of r dotted with u. So here when I plug in t equals 0, I just get the gradient of f of r. And so that, in fact, proves to us that we can rewrite the directional derivative as the gradient dotted with u. I'll leave it to you to, in fact, show that the partial derivative with respect to x and the partial derivative with respect to y can be computed in this way, where u is either the vector 1, 0 or the vector 0, 1. Okay, let's look at a few examples. Let's calculate the directional derivative of f of x, y, z is equal to x squared e to the minus yz at the point 1, 0, 1, and in the direction of u, which is 1 over square root of 3, 1, 1, 1. So here u is going to be my unit vector, and I want to compute that directional derivative. So the first thing that I'm going to need to do is I'm going to need to compute the gradient. The gradient of f, in this case, is going to be the derivative of x squared is 2x. Everything else is treated as a constant. And then the derivative of, with respect to y, is going to be, let's see, x squared e to the minus yz. And then the derivative of minus yz with respect to y is going to be a minus z. And then finally, if I take the derivative with respect to z, I'm going to get, again, x squared and e to the minus yz. And the derivative of e to the minus yz is itself times the derivative of minus yz with respect to z, and so that's going to give me a minus y. And so there we have the gradient of f. Now we're going to want the gradient of f at a particular point. That point's going to be 1, 0, 1. And so if I plug in 1, 0, 1, I'm going to get 2 e to the 0, or 2. If I plug in 1, 0, 1 to the next component, I'm going to get a negative 1 e to the 0. And then finally, I'm going to get, when I plug in 1, 0, 1 to the last component, because y is 0, I'm going to get 0. Okay, so the gradient is the vector 2, negative 1, 0. And so the directional derivative of the directional derivative of f in the u direction at 1, 0, 1 is going to equal the gradient of f, which is 2, negative 1, 0, and then dotted with 1 over square root of 3 times 1, 1, 1. The result is going to be, I'm going to pull out the 1 over square root of 3, and I'm going to look at that 2 times 1 is going to give me 2. Negative 1 times 1 is going to give me negative 1. And then finally, plus 0. And so that directional derivative is 1 over square root of 3. So what that's saying is that in the 1, 1, 1 direction, okay, that the rate of change of the function f is 1 over square root of 3. Now let's look at another example. So suppose that the temperature in space is given by a function t of x, y, z, which is 10 plus xy plus xz plus yz. Find the rate of change of temperature at the point 1, 2, 3 in the direction of the vector v equals 1 to negative 2. Okay, so we're going to need the gradient. Okay, the gradient is going to be, well, the derivative with respect to x of 10 is 0, of xy is going to be y, and of xz is going to be z, and then the derivative of yz is going to be 0. So I get y plus z. The derivative of t with respect to y is going to give me 0, x, 0, and then z. And then finally, the derivative with respect to z is going to give me 0, 0, then x and y. That derivative, or that gradient, at the point 1, 2, 3 is going to be, let's see, y plus z, 2 plus 3 is 5, x plus z, 1 plus 3 is 4, and then finally, x plus y, which is 1 plus 2, is 3. Now, we need to do this derivative in the v direction. So v is not given as a unit vector, so we're going to actually need to find the length of v. In this case, the length of v is the square root of 1 squared plus 2 squared plus negative 2 squared. So 1 plus 4 is 9, and so the length of v is 3. So here our unit vector, v over the length of v, okay, that's going to be 1/3 times the vector 1, 2, negative 2. And so if I take the directional derivative in the direction of v, so here it's in the direction of that unit vector v of t, that's going to be the gradient 5, 4, 3 dotted with the unit vector 1/3 times 1, 2, negative 2. And so that's going to give me 1/3 times 5 times 1 is 5, plus 4 times 2 is 8, plus 3 times negative 2 is a negative 6. So in fact, that directional derivative is 7/3. Okay, so that says in the 1, 2, negative 2 direction that the rate of change of temperature is going to be 7/3. So for every unit that I go in the 1, 2, negative 2 direction, that temperature is going to increase by 7/3.